Wake up. You're not retired yet.
Am I filming?
Yep.
Good morning, boys and girls. It's me again, Mr. Rosenberg, and we're going to discuss the concept of kinetic energy and work done. We know about work done as force times distance. And we also know that work done is energy transferred. So suppose the energy being transferred to a car, say, or a sledge, or a lorry, or a boat. And we wish to know the kinetic energy of the carry of the boat. However, if a car's travelling at 20 metres per second and it's got a mass of 1500 kilograms, we don't know the force that pushed it. And we don't know the distance the car was pushed over. But we do know one thing about the force. The force had to be unbalanced. That was very, very important. The force has to be unbalanced, otherwise it wouldn't have gained that speed, whatever it happens to have. And we can also assume that the heavier the car is and the faster it's going, the more work that had to be done. A light car travelling at, say, 10 metres per second won't need as much energy to get it to that speed as, say, a heavier car travelling at a greater speed. Problem is, when a car's travelling at, say, 10 metres per second, it's got a mass of 1000 kilograms, say, we don't know the force that was acting on it. We don't know the distance it was moved over. Therefore, how can we work out its kinetic energy? We need a different formula for that. So our task is this. Here we've got a car of 1000 kilograms, it's travelling at 15 metres per second. How much kinetic energy does it have? Now we know the kinetic energy that it has to come from the work that was done in the car initially. The work that was done pulling the car with an unbalanced force to that particular speed. We don't know that when we look at a car that's travelling at 15 metres per second, it's got 1000 kilograms. We don't know that information. So we need to have a way of changing our force times distance formula into a formula that we can work with, which is going to be mass and velocity, because we know what the mass of the car is and we know what the velocity is. Let's see how we do that then. First of all, we've got this situation here. We've got a 40 Newton force pulling a sledge of 40 kilograms for 6 seconds. I'm going to use what we've done before to analyse that motion and find other physical quantities that we normally work out. First of all, here we can actually see the speed changing on the table, and there's a graph drawn alongside it. What sort of things can we learn from a graph? Well, we can learn the acceleration of the vehicle, and that's clearly stated. We've done that before. Remember that starting speed is 0. Now we can find the average speed, the distance travelled by the car, and that's something, the area under that well-defined mathematical shape called a triangle. That's just half the base times the height. That gives us our distance travelled. And the other time we can work out is the average speed, not just the distance travelled divided by the time taken. Now, funnily enough, if I multiply the mass times the acceleration by the average velocity by the time taken, I get 480. And that's exactly the same as the work done. But we can't use mass times acceleration times average velocity times time to work out a kinetic energy, because we don't know these things when we can see a car moving. We just know that it's mass. We just know it's mass that it can be measured, and it's velocity that can be measured. But it's very easy to show that mass times acceleration times average velocity times time is exactly equal to 1/2 mv squared. The acceleration, remember, is the final velocity divided by the time in our situation, and the average speed is always the final speed divided by 2 in this particular situation. Multiply all these things together, you get 1/2 mv squared. Now we're in a position to solve a problem. Now the video I shall bring out next week shall discuss work done in a vertical context. So we're no longer thinking of pulling things horizontally like this, we're going to pull them vertically like this. And ask yourselves, what? Now you might be thinking to yourself then, well, what difference can that possibly make? Pulling things horizontally with a force, or pulling them vertically with a force. What possible difference can that possibly make to this? Well, that's a very good question. And I've got to say, I'm not sure either, but we'll just go with it and we'll see what we come up with. My name is Bernard Rosenberg and I'm the Young Scottish physicist.